Good morning, good afternoon, and good evening, wherever you may be in the world. Welcome to Cavirin's March webinar, Machine Learning for Cybersecurity, Hype versus Reality. We will start in about 30 to 45 seconds to allow additional people to come online. Welcome, wherever you may be in the world, to Cavirin's March webinar, Machine Learning for Cybersecurity, Reality versus Hype. There's been a lot of talk about machine learning and AI, and we want to try to put some things into perspective as it applies to cyber posture, as it applies to cybersecurity. One of the things we'll also be discussing are some of the learnings from the recently completed RSA security show in San Francisco. Just two brief elements of housekeeping. First of all, you'll see in your console that you can ask questions of the presenters. Please, let's try to make it interactive, so ask away. And second of all, for people that are here for the entire webinar, we'll go ahead and randomly draw an Amazon $50 gift card, and we'll be able to get in touch with you after the event. So I'd like to present or introduce our two esteemed presenters. The first is Praveen Jain, just recently appointed CTO at Cavirin. Over 2.5 decades of engineering and leadership experience in the networking, data center, cloud, and security spaces. I'll let you read his background on your own, but we're really pleased to have him and his expertise and his knowledge in the field of networking, policy creation, and data center infrastructure. So Praveen, welcome.
Thank you.
And second of all, Basham Anab, who's our head of product management. Also a lot of very deep experience in machine learning, in security monitoring, and cloud deployments. He's been on board here for about 1.5 years. And he's also front and center in some of the development work we've done in the whole machine learning space. And we're looking forward to his insight and expertise on this webinar. So, Basham, welcome to you.
Thank you, Dave.
So let's jump in.
Hello, this is Praveen. Welcome to the webinar. And Basham, hope you had a good coffee this morning, because I hope to grill you on machine learning today. All right, so yeah, Basham, what happens is that if I go to any security company, you'll always find two words, AI and machine learning, by default, right? So it's one of those technical word or the industry which has been just overhyped across the board, right? I'll give you an example. A few days ago, I met with a company, and they were saying, and it's a vulnerability management company, and they said that, oh, we can find where the next vulnerability is going to happen in your infrastructure using AI and machine learning. I was very intrigued. I said, that's amazing. If you can do something like that, then your problems, all cybersecurity problems are solved. So then I started digging deeper, and then he said, the way we do is, we are a vulnerability management company. We know a list of vulnerabilities out published in the web. We go to your infrastructure, scan all the hosts, and any host which is not patched against those lists of vulnerabilities, then I know that that's where the next attack is going to happen. So then I asked him, where is the machine learning and AI in it? So his answer, first of all, he could not answer. But his pretended answer was, I'm learning external list of vulnerabilities and mapping against your system. But this technology or this kind of mapping, or what I call it as a rule-based system, has been around for decades. Now suddenly everything becomes AI and machine learning, right? I'll give you a chance to explain first what is machine learning, right? So that at least we set a baseline. But before I do that, I wanted to give my example, right? Everybody talks about dog picture versus cat, and machine learning is ability to identify what it is. But let me take another example, right? Let's say I want to predict the housing price, let's say in Bay Area. We are in Bay Area today. Let's say in Bay Area. Now, there are so many factors. Yes, there are some static factors. If you live in a good school district, yeah, that's good. If you live near a grocery outlet or walking distance to the grocery places, let's say you have access to highways. But then there are factors like, is the interest rates down? Then there are other factors. If a lot of companies go IPO or start an exit in Silicon Valley, for example, chances of housing prices going high is higher, right? Somebody just puts an offer which is over the market price, and other people start comparing that we also need to get the same amount. So these are the factors, in my opinion, where you cannot apply a formula and say this is what it is going to be in next 5 years. That's where I believe a machine learning could help, where you take the historical data set, train, taking all these factors, let's say 30, 40, 50, whatever those number of factors are, you train and try to predict. Obviously, you may not be accurate. If there was an accuracy, then you can invest and make money out of that, but that's not the case. But you can train and predict out of that. Do you think this is roughly the right description of machine learning, Basham?
Yeah, so this, I think generally it fits the pattern. And as you pointed out, I think there is quite a bit of confusion between analytics, like doing a search query in a log analysis system and looking for patterns, versus a rule-based system, which you also mentioned, and and then the part around learning. So the key aspect of machine learning, in my view, really is that there has to be something that needs to be learned. So in your example around housing prices, what this machine learning system is actually doing is to actually learn the formula that is hard to express in a mathematical sense ahead of time. So if you could do that ahead of time, then it's a rule-based system. If you can't do it ahead of time and you had to learn it from the data, that's really what a machine learning algorithm would do in this particular example. And similarly, I would say for a lot of unstructured data problems, ultimately what you're trying to do is there is a so-called loss function, which is really essentially a predicted value minus the actual value. And that's what the machine learning algorithm is actually trying to figure out by learning from the data, right? So the main thing that you're looking for, AI and ML, to be honest, have been around for more than 30, 40 years. What's changed significantly compared to maybe, the last 5 years or so is the idea that the algorithms are such that they have one significant property, which is that the more data you throw at the algorithm, the better it is in its predictions, right? So that's one of the other features that you also want to be looking for in the class of problems that you want to solve using machine learning, and also testing and diagnosing if somebody's approach is actually an ML-based approach as well.
So Basham, that's a good input. That's a good way of understanding what machine learning is about. So out of all the noise, let's say there are 100 cybersecurity companies and 100 of them are claiming that we are doing AI machine learning. Do you think there are real success stories? I'm sure there is something, right? There is some smoke somewhere, right? It's not everybody is doing something wrong. So as you go along describing the machine learning, I will appreciate if you can really point out some real use cases of machine learning and how it's beneficial to cybersecurity space in general.
Absolutely. So today, do you want to advance? So basically, if you look at machine learning, I think there are essentially three broad categories of use cases and supporting algorithms, a class of algorithms where I've seen machine learning being used. I would argue that this is probably applicable to pretty much all of unstructured data. And the first kind is sort of the dog versus cat, which is really building a classifier model for detecting one versus the other. So the successful stories in the security space, at least, for more than a decade, anti-spam type solutions like email spam, they've been around. Most people don't even notice it, but these systems have been optimized over a period of time to distinguish good emails from the spam ones, and 99% accuracy or more is not uncommon, right? And
Basham, just to interrupt, right? Just so that we have the same baseline. When you said unstructured data, do you treat cybersecurity as unstructured data or structured data, so that we follow along as you're talking?
Yeah, so I would say most, pretty much all the data that you see in security, because it's all driven by logs and things like that, I would argue it's primarily unstructured. There might be a few cases here and there where you could get some structured data, but I would say pretty much everything that you see on this slide, pretty much all the success stories we've seen, including the work we're doing at Cavirin, I would say, fits in the domain of unstructured data.
Okay, great. Thank you.
So again, another example of a classifier is essentially data classification itself. So data classification is the heart of data loss prevention systems. The main problem there is trying to figure out if there is any sensitive data in your network in transit or data that's actually being stored in a database or a file system, figuring out does it contain social security numbers, credit card numbers, driver's licenses, and so on. Right? So data classification is essentially shining light on this aspect, protected or private information in your data. And there again, classification algorithms have been used quite successfully, for more than a decade at this point. And I would say 90% or more accuracy is not uncommon for those kinds of applications. So again, that's, classification, I would say broadly, is absolutely one class of algorithms and one set of use cases to which, machine learning has been applied fairly successfully over the last decade or so. The second general area is around anomaly or outlier detection. As this picture says, there is a slight distinction between anomalies versus outliers. Anomaly is basically, you're actually looking for a pattern of activity or a period of time, and looking for behaviors that are actually different. So as this picture graphic is actually showing, trying to figure out, if the normal pattern of user activity is, follows one pattern, but you have, one or more behaviors that are, outside that norm. That's what an anomaly is. Outlier typically focuses on specific hosts or specific users that are deviating from a norm. So let's take a few examples of that. So the rogue insider. So for example, let's say, most people, like in file analytics, these kinds of algorithms are fairly well known. So the idea here is that, let's say, on average, employees in your company do 10 read writes per day. An example of an anomalous behavior would be, all of a sudden, if the read-write activity goes 10x compared to that particular norm, right? So that's a read-write is a signal that you look for in terms of behaviors, and anytime you see a huge deviation from norm, that's what you would consider anomalous behavior. Again, it doesn't tell you what's wrong, but at least it brings the attention of the user to the possibility that there might be a compromise going on. Similarly, flipping that story and focusing on specific users, you can actually cluster users, for example, based on their read-write activity in my example. So for example, let's say all users in marketing, they do 10 read-writes per day in file systems, whereas people in engineering, because they're doing constant check-ins and check-outs of code, maybe they do 100 read-writes per day, right? So you could then pick users in marketing or engineering who are deviating from their norm and then say that these guys are probably outliers. So as an example, so if you have an outlier could be, in the case of file analytics, it could be somebody from marketing trying to access data that's primarily touched by engineering, for example, source code. That could be an indication of compromise, or an engineer who's suddenly doing thousands and thousands of read-write activities, perhaps because he's copying the source code for illegal purposes. That again would be an indicator of compromise as well. So all of those examples where it's some combination of anomalies or outliers in these examples. And last but not least, data leak detection, again, is a very common use case where, and by the way, these are features that are available in platforms like Amazon Guard Duty, for example, which gives you an out-of-the-box event for detecting more than the normal amount of data going out of your enterprise. So that's an example of anomaly detection applied for network traffic, which in this case, it could signal that data is being leaked from your enterprise, as an example.
So, Basham, so far you described that you are kind of figuring out an abnormal behavior, like you are doing 10 read writes per day, and now suddenly you started doing 1,000. Yeah. Is it ML or is it AI?
So that's, I think it's, I would say, Broadly, I would say that's probably considered machine learning. I think the main distinction that I've seen between ML and AI typically tends to be in sort of areas like, image analysis, video analysis, and so on, where the patterns themselves, as they call it, the features themselves are not known ahead of time. So in my example, I kind of know what I'm looking for. Whereas in the case of, the dog versus cat classification, if you look at neural networks, for example, like a common set of algorithms underneath image detection and video detection. There, the features themselves are not known ahead of time. So what distinguishes a dog from a cat is not known. Right.
So can I say that the AI is a bigger field, machine learning is a subset of that?
Correct. I would generally say that, and then data science, which is sort of that one level or an offshoot of all of these things. But data science, I would generally say, is more for it's sort of a extensive analytics where you're actually dealing with structured data. In your housing price example, that's essentially data science where you're trying to learn a model for predicting stuff from structured data. Again, it's regression analysis, things like that are just a general case of that type of data science type models applied as well.
Okay, very good.
And then the last one, which I haven't seen too many examples of, but the Cavirin innovation that we've done, which we'll talk about in a few minutes, the idea of recommender systems, right? So recommender systems is fairly common sort of in the consumer experience. So this particular screenshot is actually Netflix, where as you start using Netflix, it starts making personalized recommendations for you in terms of movies or genres of movies that you might be interested in, right? So there, the idea there is that in the case of Netflix, the data that's learning from is your own activity in terms of the kinds of movies where you express an interest in, right? So similarly, in the case of Cavirin, what we are doing, and we'll talk about it in more detail, is to actually take compliance standards like HIPAA or PCI, and then trying to figure out what sort of technical controls would best serve the intent of those kinds of compliance standards through a recommender type model. We'll get to that in more detail. I haven't seen too many examples of that in cybersecurity, but just want you to be aware. In unstructured data, for sure, recommender systems like the Netflix example, like what you see on, say, websites like New York Times or CNN, where it's recommending stories or videos that are related to the article you're looking at. All of these are examples of recommender systems, especially for unstructured data. And one last thing that I do want to point out, which goes back to one of the earlier questions, the general workflow that you'll see in any machine learning system is, you've got a set of data on which you train a model. So the train, test, predict that you see at the bottom of the slide, that's the general workflow. Training is really the act of taking a bunch of data and learning a model. In a very loose sense, learning a model is figuring out a formula that reflects what the model, what the data is trying to tell you. Then you test the data against a portion of your data set which the machine hasn't looked at. So what you're really trying to get at is, how much accuracy does the machine learning model actually have, and then the prediction is basically for new data that the machine has never seen before. You want to apply the model against new data sets and then see what sort of predictions you get. The general rule of thumb in machine learning is sort of 80-20 split. So if let's say you've got like 1 million files in your log data, you might use 800,000 of them, that's about 80%. You'd use 800,000 of them to actually train your model, and then you might use the remaining 20% to actually test the model, right? So that's sort of the ratio that you typically see in machine learning systems, similar to what we've also done at Cavirin.
I just want to remind that if you can feed in your questions, that way we can make this presentation very interactive. Otherwise, Basham will continue going. So, love to hear your questions. So, Basham, now you described all of it. I hope I understood some of it, at least what you just said. But how do I figure out what is real, what is not, right? If there are, as in my earlier example, if there are 100 companies, I'm saying they are doing, all of them are doing AI and ML, how do I remove that noise and see who is real or not? So any thoughts on that?
So again, I can't say that I have formula for you.
Oh, no, that's where we need ML. Oh, now I get it. So we need AI ML to figure out what is real, what is not.
Potentially. That's actually a good one. So, if you look at the next slide, so again, there is a framing of the problem in terms of what we see. Let me just advance it.
Yeah, sure.
So what this is showing you is essentially sort of a map of the world in terms of what goes on and the kinds of use cases that you're looking at. So the x-axis in this picture is sort of the defender view, which is defender is essentially a company, an organization that is trying to protect itself from threats of any kind. So that's the x-axis, and the y-axis is your attacker or the hacker's view of the world, which again, two levels there. From a defender's perspective, you could be dealing with known vulnerabilities, and I'm using the term vulnerability to either mean a flaw in the software, that's what patches typically do, or it could be a vulnerability could be a configuration error in your systems, or it could even be vulnerabilities in terms of specific business processes and things like that where you have loopholes. For example, you might have loopholes in your role-based access controls and so on. All of those are examples of vulnerabilities. I'm using that in a fairly loose sense. It's not specific to patches, and that's not the intent of what I'm getting at. So again, from a defender's perspective, you might be dealing with known vulnerabilities, or you might be dealing with new or unknown vulnerabilities. And then from an attacker's perspective, the two levels there is a known exploit and a known recipe. And we can talk about some of those examples, or it's a new exploit that the hackers have come up with. So those are the two broad levels here. Now, what this picture is actually trying to tell you is that even prior to machine learning, threat defense is not new by any means. But the idea there is that there are tons of techniques today with respect to sort of the non-machine learning universe, where and what this picture is trying to tell you is, what are the kinds of tools or technologies that you can potentially consider in each quadrant. So for example, vulnerability scans, kind of what Cavirin has done traditionally, and what other vendors out there also do. It's primarily dealing with known vulnerabilities for the most part, and then to the extent that you can correlate them with known exploits, you can actually make those vulnerability scans even more interesting. Pen testing is really where you're dealing with, again, a class of products that are essentially looking for known patterns of attacks and then looking to see if there are any vulnerabilities that you as an enterprise may not be aware of. Threat intelligence, which has been fairly common in the last 2 or 3 years, especially with commercial products like AWS Guard Duty coming out there. Basically, they're actually looking for again, known vulnerabilities against which there might be new exploits coming in. So, as an example, taking about, one of the things that you get out of Guard Duty, for example, is, detecting if there is Bitcoin mining running on your EC2 instances. Or another example of threat intel is, are your machines connecting to suspicious IP addresses out there and, leaking data and so on, right? So again, that's an example where, the vulnerabilities are something that the enterprise is aware of, and what you're really trying to get at is, are there new exploits for them?
So just to understand, we're still talking about without machine learning.
Without machine learning.
Oh, so far we haven't gone to machine learning.
Yeah, so the point is, can machine learning make any of these things better? That's really the next slide.
I'm with you so far. Very good.
Right, and then there is a question, we'll answer that right afterwards. And then one last thing that you want to be aware of in that sort of the zero-day attacks. Zero-day attacks typically, the top right quadrant that you see here, that's really around new kinds of exploits that are going against what the enterprise itself isn't aware of, right? So the average dwell time is of the order of 200 or 225 days. So that's what the statistics is in the industry, which means that for zero-day attacks, the enterprise isn't even aware that they've been breached for at least 200 days or more, right? So that's really where typically the root cause happens to be that there is some flaw that the enterprise isn't aware of, but the attackers have gotten hold of it. Now, the normal recipes for it, what you see here is really threat hunting is the main strategy that you want to be using, and then you want to be doing this using your SIM tool like a Splunk or what have you, and then hunting those logs for patterns of activity. Most of those patterns of activities are really around the threat hunting recipes that you see on this slide. Stride LM is one framework that you can look at. Stride stands for the S is spoofing, thieves, tampering, R is repudiation. You can read on the slide. But basically look for patterns based on that. So for example, if you're looking for information disclosure, which is the I in Stride, what you might be doing is looking for your logs and looking for patterns where there is unusual network activity with respect to data being, like gigabytes of data being transferred over the network when you're not expecting it, right? Similarly, another kind of unusual activity that's, like for example, if you look at your logs and you find that, PowerShell scripts are being, launched at startup time for your machines, that's fairly unusual because most admins don't do that. So that again is another example where potentially what that indicates is that there's probably some tampering that's been gone on for your systems, or some sort of elevation of privileges that have also gone on. The bottom line is that the threat hunting framework is what it is, and there are tutorials out there on the web that you can take a look at. Most of it involves looking for these the Stride LM type framework, and then hunting for threats. Right, this is what you pay your security researchers or security analysts for. And then network segmentation, as Praveen would point out, is really a sort of a proactive strategy where it prevents network traffic by definition by closely cordoning off your assets within microsegments, if you will. So that prevents network activity, and then similarly, and if that's there, then any chance of lateral movement or information disclosure is minimized, right? So again, these are all proactive examples of what you can do without machine learning.
So there's a question, but maybe what I'll do is, let's address that question in a section where we are already addressing some part of that question, so we'll defer it for now, but thanks for putting in the question. We'll continue going for now. Yeah.
Yeah, so if you look at machine learning, so hopefully machine learning improves the same picture, and and this is really the core of this webinar, if you will, in terms of what's the hype and what's the reality. So what you typically find is that in successful examples of machine learning, you're probably dealing with systems that are trained using known attack patterns, known exploits, and known vulnerabilities. Though there the algorithms do work well. Now the examples that I gave a little bit earlier on with respect to whether it's anti-spam, data classification, the examples that Cavirin that we've done here locally as well, all of those sort of fit in that pattern. It's sort of the known exploits, known vulnerabilities, where you can actually, there is data sets available that are actually labeled for the kinds of exploits that you might be looking at, and it's easy to train an accurate model in those contexts. Where it gets a little bit hazy is in the other two quadrants, where you're dealing with either known exploits against unknown vulnerabilities, right? So again, the point is what the attack patterns are going to be, so potentially you can train on those, but it's the unknown part of it is the kinds of vulnerabilities that you have, right? So that's the reason it's yellow. And similarly, when you have known vulnerabilities but new exploits, by definition, you don't know what those new exploits are. So there is hardly anything for a machine to get trained on, right? So the point is the idea that you can actually come up with a classifier in these kinds of contexts which detects a breach situation versus a not breach situation is highly unlikely, right? So, but we can talk about other kinds of ML approaches where it can potentially work. And the last but not least, where you're sort of dealing with the unknown unknowns, if you will, the chance of ML, especially classifiers being trained on breach versus no breach type situations is close to zero because there is absolutely nothing to go by. But is that game over? It's not, right? So what this picture is actually trying to tell you is that if you have specific machine learning techniques or algorithms that are complementing what you saw on the previous slides in terms of traditional approaches, that's where I think you'll get the extra level in terms of productivity. Because ultimately what you're really looking for is Are you better today than yesterday in terms of your threat hunting capabilities? Are your operators more productive than before in terms of their own ability to do their job, right? So the main guidance here is that I would say if your vendor says they're sort of in that green zone in terms of getting trained on known exploits and known vulnerabilities, I think they should absolutely think that ML is going to do the job for you, possibly better and at a greater scale than previous approaches. Whereas in the other quadrants, anomaly detection is the main, I would say anomaly detection is the main technique you would use in the yellow and red segments, but you have to augment that with things like threat intelligence, which is on the previous slide, or threat hunting techniques as well.
So Basham, now you have described the baseline of what is machine learning, what is AI. Now, how do I figure out whether Cavirin is among the noisemakers or they have a real thing inside the AI ML?
Preferably, I would say, you be the judge.
Yeah.
Right? So let's talk about what we actually did, right? So yeah, go to the next slide. So Cavirin's business, one part of what we do is really around helping organizations get a sense for where they stack up in terms of their overall security and compliance posture. Now, we do that using a proprietary SelfBoss scoring algorithm, if you will. And the gist of it basically is that we look at your infrastructure. So in our case, what we mean by infrastructure is essentially a collection of resources in multiple clouds like AWS, Azure, and GCP, along with on-premises assets like compute instances running on premises, along with some level of Docker containers as well. Now,
so you're saying that you can do hybrid, on-prem, cloud, Docker, everything in one portal?
Essentially, yeah. And what we actually do is vulnerability and config management for that type of hybrid heterogeneous infrastructure, if you will. Now, like I said before, our main value add is really around the idea that actually I can score the risk associated with your hybrid infrastructure to come up with what we call a SelfBoss Score. It's just a number between 0 and 100. 0 means you have the most amount of risk in your infrastructure, and 100 means you have the least amount of risk. And it's a simple way for CISOs or security analysts to see how they're doing at any given point in time, and then see, compare that from a trend line perspective from a previous point in time. And then more importantly, if I want to improve my cyber posture or security posture, what are the steps that I need to do? And that's where the ranking algorithm that we come up with in terms of gaps in your security posture and how you can address that, those are actually ranked using the cyber posture algorithm.
Again, can I think about this as a credit score? Like I have a credit score, it tells me how good I am. Can I say that?
I would say it's similar in the sense that it's similar in two respects. The first respect is that as a user, it's just a number, and in that sense, you essentially boil the ocean, just like a credit score. Organizations, they base the credit score on 20 or 25 different signals of, consumers' credit worthiness. But the end result, though, as a lender or as a consumer, it's a simple number that you can take a look at and see how you're doing, right? So that's absolutely, from that perspective, the SelfBoss Score has that same simplicity for the user, even though it's based on fairly complex signals underneath the covers, right? So that's the first thing. And similar to a credit score, I think if you go to a credit consultant, I think they can probably look at your credit score and tell you. In fact, all the credit rating agencies also tell you how do you improve your credit score, take these particular actions and so on. Similar to that, our remediation guidance, as we call it, is similar in that sense, in the sense that based on the greatest impact on your security posture, what are the actions you can take right now, and what's the sequence in which you will do them based on improvement potential, as we call it.
So in other words, you're trying to find credit score of a company from the cybersecurity perspective using AI ML, which you are going to explain, and I'm going to evaluate whether it's a noise or not.
Okay.
That's the ballpark we are in, right?
Yes. So in our case, again, the recommender system, basically what it's actually doing for us is, like I said before, ultimately, Cavirin is a software that needs to evaluate the infrastructure. So what it actually needs is a set of technical controls, as we call it, that we can try against your AWS resources or your GCP resources or your on-prem resources or your Docker containers. That's what we're looking for. But then the flip side of it is that if you want to prove a compliance posture, for example, if I'm an organization in the healthcare ecosystem, in this example, I want to demonstrate that I am compliant with the technical safeguards for HIPAA as an example. How do you do the mapping? So the general problem here is that there is a set of plain English requirements that the compliance standard like HIPAA is specifying for you, right? So what you see on the left-hand side is actually pretty much all there is in the technical safeguards section of HIPAA, with respect to access control, audit control, integrity, and so on, right? So these are general descriptions of requirements, except you do not know, and it's not the job of the benchmark to tell you how to actually evaluate it against a Windows machine or an Ubuntu machine or an AWS storage bucket or what have you. So that's the mapping problem that you see on this slide, which is how do I take a plain English standard and then map it to a set of technical controls that a machine like Cavirin can actually evaluate. So mapping is the first aspect of what we solve for. The second part is what you see in this picture is that each of these lines that are being drawn from the left-hand side to the right-hand side, from requirements to technical controls, they need to be weighted as well. Weighted as in what's the relative prioritization of a given technical control given the spirit of a standard like HIPAA, right? So for both of these problems, we essentially used machine learning. So for mapping, so the mapping algorithm is basically, I would say it's in the broad class of data, text clustering as well as similarity analysis. So that's, there's a range of algorithms that are sort of published out there that we used. And then for the weight assignment, we actually use the neural network, right? So, and then you put them together in one box, if you will, to achieve the outcomes you're looking for. Like what is the mapping of technical controls to requirements, and then what's the relative importance or weights, if you will, of those technical controls, given the spirit of a standard like HIPAA, right? We put them together and then put them in our, and these are essentially inputs to our SelfBoss scoring algorithm itself, which is on our next slide, right? Right. So if you look at our SelfBoss scoring algorithm, it's sort of a layer cake that is essentially inspired by NIST, NIST cybersecurity framework. So, so going bottoms up, so the main inputs to this is tell me what vulnerabilities you have in your infrastructure, what is the weight associated with those vulnerabilities, and then we come up with a scoring algorithm for that at various levels in your infrastructure. So the levels being, you have a company level score, you've got a asset group level score, you've got a resource type level score. So for example, if you want to know how am I doing on storage versus compute, you can do that. If you want to know environment level scores, how am I doing in AWS versus GCP, you can do that. And then all the way down to an individual resource like a single storage bucket or a single EC2 instance, you've got a score at that level as well. The general idea here, the score is what it is, but the main action or insight that it drives is how do I improve the score at each of these levels, if you will. Right? So again, I don't want to get into too much details here, but the general idea here is the ML algorithms that we used are essentially informing the inputs that go into the scoring algorithm itself.
So I know we are receiving the time warning,
yeah.
But I just wanted to quickly ask you, none of this could have been done with the rules-based engine. Why ML and AI in this?
Yeah, so great question. To be honest, Cavirin has been in business for a while, and we did all this only in our last release, which is literally the last 3 months. So for sure, this can be done without ML. It has been done. It was done without ML. In fact, the way it was done without ML was actually we hired a set of security experts that actually did the mapping by hand using spreadsheets and so on, right? So the main challenges, just to cut to the chase here, is that when you've got 2 or 3 experts that are essentially doing a mapping, let's say from HIPAA to a set of technical controls, there are 2 broad classes of problems that happen. The first is there are, errors in just user errors, if you will, and the second is errors in judgment. So, for example, Dave and I might be looking at the HIPAA standard, and we might come up with completely different interpretations in terms of how to interpret HIPAA with respect to technical controls. So we saw a lot of these kinds of, inconsistencies, if you will, over a period of time. So, over a period of, 2 or 3 years, successive standards, like where you see similar requirements being spelled out in PCI versus HIPAA, we saw some inconsistencies. Within HIPAA, for example, we also see inconsistencies in the way requirements are being interpreted. And so what machine learning gave us really was essentially helped us validate where we already had mappings. Did the humans did a good job, or did they make errors? So we validated that and corrected wherever we had issues. And then for new standards, which we want to do, we have a system that actually automates the process for us in a much more productive way than before. So just to give you an idea, mapping compliance standards takes about 6 to 8 weeks for a really well-trained, fairly expensive human. With a machine, you can actually bring it down to less than 1 day, right? And we keep in mind that there is human review required in all these use cases, and we'll talk about that in a little bit. But that's the cost. You don't eliminate all the costs, but you make it significantly more productive than before.
Okay. So with that, I have been holding on to a question from the audience. The question was, at the AI level, how would you test the AI platform to figure out if the info it produces is valid or not? In a nutshell, that was the question. And that also brings me to my section. How do you avoid false positives while you are doing this AI/ML implementation?
Yeah, so I think you need to have, the bottom line is that you need to have a formal definition of how you want to measure or benchmark the accuracy. I think that's the heart of Praveen's question, as well as the intention behind the audience's question here as well. So, and I think, machine learning is somewhat unique in the following sense, right? So, just to give you this quick clarification and definition. So, false positives is essentially like a false alarm. Like, you did some analysis, the machine says you have a problem, and then the user goes in, does some fact finding, and then finds out actually that is just a false alarm, there was no problem. The problem with false positives is that it's more costs for the operators. That's okay, I think.
How about false negatives?
Yeah, false negatives is the killer in cybersecurity, because the hacker needs to be successful just once against the infrastructure, whereas the operator needs to be defending successfully every time, right? So that's the balance. So the asymmetry in cybersecurity is that your attackers need to be failing you just once, whereas you need to be protecting yourself every time against them. So this idea that the cost of false negatives is extremely high compared to the cost of false positives. Right? So either way, what you're looking for is, coming up with a formal measure that balances these two outcomes, most likely, concentrating more on the false negatives and weighing the false positives less, right?
So Basham, I know we are close to our time limit.
Okay.
Any summary? Can you summarize what we talked about
absolutely.
so far?
So absolutely. So have a formal accuracy measure, and then back to the audience's question, benchmark your vendor or your algorithms against that measure, if you will, right? And then, and the main idea there is, you need to have a series of validations. Validate your training against that accuracy measure, validate your test data set against that accuracy measure, and then for good measure, you probably want to, continuously learn as well. So as you benchmark the accuracy of unknown data sets as well, and you want to be, machine learning is absolutely a continuous process. You should see models being tweaked over a period of time to improve their accuracy as they get exposed to more and more data, more and more unfamiliar conditions, if you will. Right? So in summary, my last slide here. So again, as you saw on this particular slide, go back to that 2x2 matrix. There is a regime in which machine learning is expected to work well. Right? So keep that in mind. For all other contexts where there is less data to learn from, you have to augment existing approaches, whether it's, the common strategies of threat intelligence feeds, threat hunting recipes, you need to augment those with machine learning. And I think the one that has the most amount of promise is really around anomaly and outlier detection as a broad class of ML algorithms. And then last but not least, like I said, given that the accuracy is what it is, you absolutely have to plan for the operating level for the foreseeable future.
Thank you, Basham.
Absolutely.
This is great. I think I learned a lot.
Thank you.
So, Praveen, Basham, thank you very much. Great background on the field. For those online, once again, Bright Talk will post it within the next hour if you want to review the webinar. Just a couple assets for you to take a look at. Praveen did a very thoughtful article covering some of this on Forbes Technology Console. There's a link here. We have a great white paper on machine learning-based scoring, on Cavirin cyber posture scoring that goes into some details on what Basham talked about with regards to how we do our scoring algorithm. And then last but not least, if you'd like to try it for yourselves, kick the virtual tires, we're available on the AWS, on the Microsoft Azure, and on the Google Cloud marketplaces, 14-day fully functional free trials. So once again, thank you very much for your time this morning. Thank you very much again for our presenters, and have a great remainder of your day.